Thank you very much, and thank you, Peter, for the kind introduction. In fact, I think we should all give a round of applause to Peter for all the work he's done in bringing us all together. So, my name is Tyrone, and I'm a software engineer at Facebook in London, where I've been for the past year. I'm originally from Canada, but I make my home in the beautiful city of London in the beautiful continent of Europe. So yesterday you heard from my colleague Ali about the challenges we face in cross-platform developments. And you heard from my colleague Connor about the parse framework, which makes cross-platform developments a bit easier. So today I'm going to say, forget about cross-platform. Let's talk about Android for a second. And let iOS developers worry about iOS problems, like their declining market share. So I'm going to talk about images. So how many of you use images in your apps? Lots of you. How many of you have problems with images in your apps? Again, lots of you. Good. Tell me about some of these problems. What's the problem with that? Out of memory error. Okay, yes. I know the feeling very, very well. What are the problems?
Caching.
Slow memory allocation. We're going to talk about that. Anything else?
Caching.
Caching. We're going to talk about that too. All right. So pick the right time. So what we did in Facebook is we made some changes to the way we are dealing with images in our application. And then we measured the time it takes, on average, for users to load images. And we found that we can cut that time in half. 50%. So if a user used to take 1 second to download an image, they're now taking half a second. Now most users are not going to notice this, but it adds up. We have hundreds of millions of users. And we have users spending half an hour a day, every day, going to Facebook and looking at image after image after image. And if you do the math, dozens of images times hundreds of millions of users, times half a second each per image. That adds up to more than a century per day of human time that is saved by the techniques I'm going to present in this talk. So, that's all very well, you say. How do I know who's telling the truth? Well, let me give you a demonstration. Let me see if this actually works. Does it? It does, okay. Whoops. So the one on the left is a crippled build of Facebook, taken without these changes, and the one on the right is the production version of Facebook that most of you should have on your devices now. So see how much gray you see on the left and compare it with the one on the right.
Which one is the one we have?
The one on the left sucks, doesn't it? That was Facebook as recently as this summer. All our users suffered from that. Now they don't. Now look, we should have seen that image already. It's already been downloaded once, but we're seeing gray boxes again. It's not perfect when you see it, but you get the idea. So that is what we did. How did we do it? So the first step is to think of imaging as a pipeline. You're not just taking an image and rendering it on screen. That's too easy. The first thing you do is you have to download it from the network. So you have to create an HTTP request, send it over the wire, process the response. But as we heard from the talk yesterday, you should never ever put a network request on the UI thread. Bad idea. So you have to have a separate thread and a separate thread handoff. Send things to the network environment. But whatever you get back from the network is going to be compressed. And you can't show a compressed image on screen as is. You have to decode it. So from JPEG, or WebP, or PNG, or even GIF, for God's sake, you decode that into a bitmap. Sometimes you need to transform the image. We don't do this a lot for images from the network. We do this mostly for images downloaded from local file. But if you need to crop an image, resize it, or scale it, it's best to do so with a compressed image. You're not doing a compressed one. Faster. But it would be foolish to download an image from network every single time, right? So you have to do a cache. We call it disk cache, even though it's really internal storage. Fewer syllables that way. But even disk operations are expensive. You have to put them on a separate thread as well. So we have a level 2 cache, a memory cache, that you can hit on the UI thread before you go off the disk. And so it seemed to be at first a very simple operation just putting an image on the screen. It is actually a sequence of a lot of distinct operations that have to operate in different threads. And the first takeaway we discovered is it's very important to think of these as distinct operations. Do not use the same thread pool to read from your disk cache as you're using to read from your network, as you're using to do CPU-intensive operations. You're going to have a bad time. Imagine if you had a pool of, whatever, 10 threads that are downloading images from network. And let's say they were all busy downloading images. And then you have the user request an image that happened to be on your disk cache. If you're using the same thread pool, then the network requests are going to block a request on disk. That would be mind-numbingly stupid. Since the whole point of having a disk cache is to avoid going up the network and being blocked by the network. But if you're not careful on how you separate your threads, and we have some bugs in how we separate them, you're going to have that problem. And when you fix that problem, you start to see performance improvements. Likewise, protect your CPU. CPU-intensive threads have to be separate from IO-intensive threads. So just thinking of what you're doing as a pipeline, as a series of stages, a series of operations, rather than a single monolithic operation, is going to make a difference in the way you build your code. But this was not the primary gain. The primary gain was confronting the garbage problem. So, how many of you write your applications mostly in Java? Almost everybody. How many write them mostly in C++? One person. You are a very smart man. I envy you so much. And how many do a mixture of C++ and Java? Yes, you're also very smart people. We probably should have done that too. But for those of us stuck using Java, because Android said use Java and most of their libraries available in Java, we are stuck that Java is basically garbage in, garbage out. And garbage is a very, very expensive thing. So let's talk about the heap for a second. The heap that we have on Dalvik is a very dangerous one to use. The way Dalvik handles memory is, every time you call the new operator to allocate memory, it tries to see whether you have enough memory. So it doesn't even look at the physical memory of the device. It looks at the Dalvik heap, which is a limit, which is maybe about 1/10 of your physical device memory. And if it cannot find enough memory, it tries to run a concurrent garbage collection. So this is supposed to avoid blocking your threads, but the truth is most of the time it doesn't work. It will fail. And then Dalvik will stop the world. Every thread in your process blocks while it is doing a garbage collection, including the UI thread. So you can have a user who's scrolling through Facebook, all he wants to do is see his cat photos, and he goes up and stop moving. What the hell? And this is going to happen more often, of course, on devices that have less memory, on devices that are running older operating systems, in short, the majority of our users. And he's not going to blame Android for being built this way. He's going to blame us. He's going to write a hostile review in the Play Store, or a sarcastic blog post in TechCrunch, and complain to his friend who works at Facebook, and how much Facebook sucks. So that's what you get if you're using the Dalvik heap. In contrast, there's the native heap. Now, the native heap is just beautiful. There's no garbage collector. So you can allocate memory as you please, and it's fast. You are not bounded by the Dalvik heap limit. You are bounded by the physical memory of the machine. So you can allocate as much memory as you want. You can do so cheaply, but you have to manage it yourself. The garbage collector is not going to come and save you. If you don't free your memory, then you will use it more and more and more until Android treats you as a rogue process and decides to kill you. That is, it sends you a kill signal. And your process will die. And it will not even send a crash report before it dies. It will just disappear. The user does not even get a dialog. It's as if you weren't there. You have to start all over again. Or, heaven forbid, the user will say, oh, this app is screwy, I'm going to use another app. But the trouble with native memory is it's really meant only for C++ applications. So you can get to it easily using the C++ new operator or the cmalloc operator, but how do you get to it from Java class? Good. So here is how we're going to talk about that, native memory. So how many of you have used the Java native interface? Okay, a few of you have, and a lot of you haven't. If you are not using it, start. It is very, very useful if used properly. So all you have to do is declare a method, an ordinary method, except it has no implementation, and you put the keyword native on it. And what this method does, the terminology is a bit confusing. You can ignore JNI export and JNI call. Those are preprocessor macros that mean nothing, except on Windows, which doesn't concern us. Then you have Java, your packaging class, blah, 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 copy to native. The first two arguments, the first argument is standard, it just means the Java native environment, or interface environment. The second argument is just the this object. whatever method of the class you're sending, and the rest of the parameters. So all I'm doing is I allocate a C++ array, and the get byte array region copies the Java array into the C++ array. And likewise, there's a similar method, set byte array region, which allows you to get the information in the other direction. And there's also set car array, there's set int array, set long array, whatever primitive you want. And that returns a C++ pointer, which you just cast back to an int, and then you have that C++ pointer sitting in your Java code. And as far as Java is concerned, you now have a large block of memory that looks to Dalvik like a 32-bit int. And you can have as much memory as you want, hiding safely away in the native heap, and the Java code does not need to worry about it. An abstraction that's very useful here is to use pools. You can use this for Dalvik, or you can use this for native memory. In a pool, and the implementation of this is fairly simple, so I'll skip over it. You should be able to get an object and specify a size, and then when you're done with it, release it back to the pool. In using the methods I showed in the previous slide, you could build a stream. You could build an input stream to read from native memory. You could build an output stream to write to native memory. And all the right methods would be doing is doing those set byte array, get byte array region calls that I showed you before. So if you did that, you could have a pool made up of native memory chunks. A fixed size pool, so you don't have to worry about using too much memory or using too little. You just have it there. And you reuse the memory as you need it. You can have streams that write into it, streams that read from it. And then you can connect those to your image operations. So you can read from network directly into native memory. You don't need to touch the Dalvik heap at all. You could read from cache directly into native memory. You don't need to use Dalvik memory for images at all, except for one stage, which I'll get to later. And so with all your intermediate steps in the pipeline I showed you using native memory, all the garbage collections that would be triggered by loading JPEGs, by sending them down to the cache, sending them up from the network, all those disappear. And those are some of your biggest allocations. But even that was not the main win that we discovered. This was the main win, pinned purgables. So how many of you have used purgeable bitmaps before? One person. Okay, so I'm going to talk about something nice and obscure. So in other versions of this talk, I've actually gone into Android source code. I'm going to spare you that here, but I'm going to show some more code samples of how we use this. So most of you have probably seen the bitmap factory class. You can decode a byte array, you can decode a file, you can decode a file descriptor, and you can pass options to it. And Android provided one option called in-purgeable. In just means input. Purgeable means this is a purgeable bitmap. So what does that mean, anyway? To really explain this, I'm going to talk about a special heap. It's part of what Android calls the other heap, and it's called ASHME. This stands for either Android shared memory or anonymous shared memory, depending on what version of the docs you use. It's not actually shared unless you send information about it to another process, which we don't do. That's not the important point. What is important is how this memory works. Instead of having allocate and free operations, like every other memory heap knows in, it has three operations. You allocate the memory, which simply creates it as part of that heap, but it is not reserved for the exclusive use of your application until you pin it. Once you pin it, it behaves like normal memory. It belongs to your app, no one else can write to it, the system will not free it until you unpin it. The difference between an unpin and a conventional free is that when you unpin, your data is still there. It's almost like a cache, and if you pin it again, it's locked again. And only if the system needs memory does it actually free the data. So the system, if ever it needs more memory, it looks first for memory that is unpinned. And if it contains data, that data is purged and discarded. But if the system never needs memory, you can unpin your data and then come back to it later when you really do need it. So see the application of this in a bitmap. You can allocate the memory at the very first step. But you only need to pin the memory when you're actually drawing it. So if you're downloading dozens of photos, as Facebook does, the only ones that actually need to be decoded and in memory at one time are the ones actually on the screen. So if we're using in-purgeable, the only decoded images are the ones that are pinned. And the decode operation happens on the pin. And as soon as you stop drawing, Android will unlock the bitmap for you, and it can be purged if you have memory pressure. So this sounds almost like a perfect solution, doesn't it? So the image is not living in the Dalvik heap, it's living in the ASHME heap, which behaves like native. The memory is managed for you. You only have to re-decode it if you actually have memory pressure. It seems like it solves all our problems, doesn't it? And we did implement this. And for a while, in fact, the example I showed you earlier was using this, the purgables. And we discovered that we had problems. We had problems in Facebook, we had problems in Messenger, we had problems in Instagram. And the problem wasn't that images weren't working, it's that every so often the UI would stutter. We would notice frames were being dropped. You could see when you're scrolling through the feed, it wouldn't scroll smoothly, it would go like this, as if it was drunk or something. And finally we went to Google and said, what's the deal here? Why would it behave like this? And they said, you're using purgeable bitmaps? Let's get back to you on that. Then we got an email saying, you know, that code is kind of old. We haven't really looked at it in 3 years. And then they added this. They actually added this a month after that email thread. And you can see in the Git history, this was added to the Java docs of the bitmap factory options. And it basically says, don't do this, because you're doing the decode on the UI thread. Remember I said earlier, don't do CPU-intensive stuff on the UI thread? That's what's causing the drop frames, because when it's putting a bitmap on the screen, it's stopping the UI thread to decode. So they say, don't use in purgeable, use in bitmap. He said, in bitmap, let's take a look at that. And we discovered some problems. Problem number one, it does not support gingerbread. How many of you have apps that run gingerbread? That few. The rest of you have moved on, you lucky devils. We would so totally love to move on from gingerbread. However, this is Facebook. The number of users we have on gingerbread is greater than the entire population of Scandinavia. In fact, I think Scandinavia plus Belgium. That's how many are on gingerbread. It's just us. I'm not saying people in Scandinavia are on gingerbread, I certainly hope not, but there is a lot of users who are using gingerbread phones, who are using old single-core gingerbread phones with 16 meg heat, for heaven's sake, but of course they got to see their cat photos, and so they're using Facebook for it. So we're not going to abandon those users. Whatever solution we come up with has to work for them too. Second reason is, even on later platforms, this in-bitmap flag is a royal pain in the ass, because the bitmap you reuse has to be the same size. In-bitmap, I should explain what it is. It's basically a pool. It's a pool concept. You decode into an existing bitmap, so you don't have to allocate memory again. But the bitmap has to be the exact same size, same height, same width. If it's 1 pixel bigger or smaller, no can do. So that's not very useful to us. We have lots and lots of different image sizes. If people upload pictures to Facebook, they care a lot about the aspect ratio, and they get mad at us if their aspect ratio is changed. So we reject this advice from Google. Ignore it. We are going to do it our way. And this is how. So we wrote another native method. We're going to call it pin the bitmap. Pin the tail on the donkey, we're going to pin the bitmap. So we discovered a function in the Android native development kit, which was just tailor-made for Facebook. Oh, I'm kidding. It wasn't tailor-made for Facebook, but it might as well. It's called Android bitmap lock pixels. And as it turns out, that's the exact same method the drop system was using for purgables to lock. But because you can get to it from the NDK, we can just pin the bitmap whenever we want. And it stays pinned until we decide to unpin it. So suddenly the draw system is not in command. We're in command. We can decode the image off the UI thread. We keep it in AshCon memory, fully decoded, and only when we say we're done with it do we discard it. So the stutters are gone. And we're in control again. So all you have to do is the same code you had in the previous image. You decode the byte array, you have a purgeable option, and then right below it you pin it. And the pin bitmap forces the decode to happen on the spot. And the only constraint is, and I'll get to this later, when you are done with the image, you have to call recycle. Otherwise, you're going to be eating up AshCon with fully decoded, uncompressed bitmap images. Remember how big bitmaps are. Even on a small device, 480 by 800 by 4 bytes per pixel is 1.5 meg. You don't want that sitting around in a device that only has 16 meg of memory. But still, this gives us everything. We're off the Java key, we're off the UI thread, performance is smooth and functional. But if you don't call recycle, if you think like a Java programmer that the GC will take care of it, bad things will happen because you will run out of AshCon and your app will crash and burn, and your manager will come to say, I thought you said this is going to solve our problems. So it doesn't. So when are you done with it? You might say when you scroll off screen. That's true, but what about the cache? Oh, you might say, I'm done with the image when it's evicted from cache. That's true too, but what if it's on screen when it's evicted from cache? So you have more than one user, so you have to count them. earlier this year when one of my colleagues came to me and he said, we're going to have to implement reference counting. I gave him this look and I said, are you out of your mind? This is not C++. We don't have a destructor. We don't have a copy constructor. We cannot give automatic reference counting the way they do in C++. And he said, use your head, boy. We are Facebook engineers. We can come up with something that will work for Facebook engineers at least. I said, okay, well, let's see what you come up with. And this is what we came up with. We can't match C++. C++ makes it automatic. This requires developers to show some conscientiousness. But what we came up with was the idea that if we can't give people syntactic sugar to make it automatic, can we come up with idioms that come naturally to the way people think so that they will just do it out of force of habit, and they will do the right thing and increment and decrement the references in the right place. So our class, I'm not going to show you the full code here because that would be much too big with all the various if statements and validations to be shown on these slides. This is what you might consider skeleton code to get the algorithm. So if you're wondering how come this case isn't handled, that's why. So let's say your object implements the closable interface. We use that as convenient shorthand because it has one method called close, which could be used to release any resource or free a bitmap or whatever you want it to do. And you had an int with a reference count, and you could get the value out from the object. And you could add a reference, increment the count, and you could delete a reference and decrement it, and when you got to 0, you nuke the object. Again, fairly straightforward. You wrap that in another object, let's call it closable reference. And this one has a marker, whether it's closed or not, and it keeps a copy of the shared reference. But more importantly, it's also closable, and it is clonable. The Java clonable interface, which is usually considered a bad thing to use unless you do it carefully. And so what you do is in the clone objects, or in the clone method, is where you add the reference. And then you pass the shared reference to another instance. So all the instances of closable reference that are representing the same underlying object are going to have the same underlying reference count. And then when you close each one, that particular instance is useless, and you've decremented the master reference count for that underlying object. And if you're closed, that instance can't be used anymore. And when the last guy is closed, the reference count is 0, your object will be deallocated, everything's happy. So all you have to do to use this properly is, if you receive a reference and you're not holding on to it, you just treat it as an object and pass it through. No problem. If you're going to keep it in some form, if you're going to assign it to a member variable that is going to live, then you cannot just copy it like that. You have to clone it. And that's all you have to remember to do. Add that .clone in the right places, and you'll be taken care of. And so, of course, my colleague was right, and I was wrong, as usual. We did figure out a method to make reference counting work, and although we've had lots of bugs over the months since we implemented this, reference counting has not been a problem. We have not had issues with objects not being allocated, or being recycled too soon, or being not recycled at all. Things have just worked, and that's been quite a relief to have. But I was hand-waving a bit when I said all you have to do is clone images when you're done with them. When are you done with an image? When it is? When you release the memory. When do you do that?
When you delete the image.
When is that? You don't know.
You don't have references to this image.
Well, when would you drop the references?
You can use phantom references they have.
Oh, no. When you don't have references, that's too early. We want to drop the image when the user is done with the image. So, as soon as the user has scrolled the image off screen, we want to drop it. Right? If you need it again later, you can get it back from cache. That's why we have an image. So you have to be able to detect when it goes off screen. And you can implement scroll listeners and God knows what else to do really complicated logic, but that's hard to get right. And Android provides hooks that are, I won't say they're easy to use, but they're easier to use than scroll listeners. So the previous talk talked about on attached from window and on detached from window. You have to use those, that's part of it. But that only applies the first time a view is attached to the drawing screen. So how many of you use list views and grid views? Quite a lot of you. So most of you may have heard that the way Android deals with list views is it recycles the children. So if you have a list view and you're constantly scrolling through it, the same children are reused over and over again. And they're sent to an adapter and down with different data. So to tell you when it's about to recycle an image, there's a method in the view class called onStartTemporaryDetach. And at first we thought, aha, onStartTemporaryDetach. That means the object is no longer on screen, we can move the image. It turned out that was wrong. Roughly speaking, what it meant was there's on start temporary detach when you might soon be going off screen, and on finish temporary detach, which actually means that on start I sent you earlier, don't ignore it. We're going to keep this view in memory after all. So what you have to do is something like this. On the on start temporary detach method, you set a flag and you defer the close. You don't close straight away. And if you have on finish temporary detach, you clear the flag. And then the defer close method looks like this. You have to post a message to the UI thread, and that will execute within that same looper loop. And you tell UI, if I'm still marked as detached by the time you execute this, then kill me. But if I'm not, leave me alone and let me display another frame. And once we did this, things started to finally work. And it took us a long time to come up with this formula, but we're still using it, even though it looks really ugly. Now this implementation you couldn't use as is, because if you notice, you're posting a message per view, which you really don't need to do. You need to post one message that'll go through all your views. But again, that's more complicated than I'll put in a slide like this. So to sum up, how do we improve image handling in Android? Put your intermediate byte buffers in native memory as much as you can. Pin all your variables and use them properly. Make sure you're freeing objects at the right time, as aggressively as possible, or bad things will happen to you. Follow these 3 simple principles, and we promise you too can cut your images in half and maybe save a century a day. Thank you.
That was great. Even I could learn something. That's great. Questions?
I have 2 related questions. The first one would be, by using Ashman, did you still have problems with fragmentation of the memory? Because I think the last problem with Velvet was that there was actually enough memory to allocate bitmaps, it's just it was so fragmented there was not enough consecutive memory. So the GC has to run. And the related question would be how much of this is still going to be useful with art? Because I think in art they really optimize in these cases with like large object, even stuff like running a defragmenter and
Yeah, so Ashman is only going to be as fragmented as you have memory being allocated files. And in our application, hardly anything else is in Ashman except bitmaps. So we don't really have to worry too much about that. Large objects suffer more from the fragmentation problem than small objects do. It's easier to find, 1 kilobyte of memory than 1.5 meg. So the large objects are hit the hardest by in the first place. As for arts, a lot of the problems in our app would be solved by arts, but arts it's kind of like Android 4.x was a few years ago. It is something that nobody is using now. It will take years to be used. Eventually, we will talk with Jelly Bean in the same tone of voice we now talk about gingerbread, but that day is not yet come. So arts is not something we can take advantage of.
More questions? Kevin?
I'm good. Could it be considered a failure of the Android system that is, such a common use case as scrolling through images is so hard to implement?
Well, to be fair to Android, they were designing for the hardware that was around in 2008. And so much of the problems are the fact that the garbage collector has only one, what we call generation. If you're using the Sun virtual machine, it has a young generation and an old generation, which handles large images, large objects a lot more easily. So you can allocate freely and not have an expensive cost. You couldn't do that on Android hardware in 2008 because there just wasn't enough memory to copy things around to generations. Again, art, I think, does have generational garbage collection, so we solve some of these problems.
Okay, are we good? One more?
Yeah, one more. Do you guys also use second lead? Because I heard of applications that use a separate process. They download the process images in the background on a separate service which runs on a separate process, which is a separate application.
How many of you would like Facebook to use, when it's in the background, to be downloading images on your device?
I'm not saying this is the supposed way to do things, but I heard that.
Well, there's a very good reason we don't do that, because users would be curious and they would do it.
One last question?